Now let's consider two molecules. Ethanol, CH3CH2OH, and also acetic acid, CH3C, and it has a carboxylic acid functional group. So it looks like this. Which of these two molecules do you believe is more acidic? Ethanol on the left or acetic acid on the right? Which one would you select? It turns out that acetic acid is more acidic, plus you have the name acid in it. The pKa for acetic acid is 4.76, and for ethanol, it's 15.9. A compound with a low pKa value is a compound that has or that is a stronger acid. So keep this in mind. As the pKa decreases, the acidity increases. So strong acids have low pKa values, and weak acids have relatively higher pKa values. But now, why is acetic acid so much more acidic than ethanol? Well, there's two reasons for that. But before we get into those reasons, let's talk about the conjugate base of each of these molecules. To draw the conjugate base, simply remove a hydrogen and add a negative charge. The conjugate base of ethanol is known as ethoxide, and the conjugate base for acetic acid is the acetate ion. Now, we said that acetic acid is a stronger acid. With this information in mind, which one is the stronger conjugate base? Is it the ethoxide ion or the acetate ion? Which one would you pick? It turns out that ethoxide is a stronger base. Keep in mind, the stronger the acid, the weaker the conjugate base. And if you have a weak acid, it has a relatively stronger conjugate base. So because ethoxide is a stronger base, that means that acetate is a weaker base and it's more stable. You'll see this throughout organic chemistry. An acid is a strong acid whenever its conjugate base is very stable or weak. So what makes this conjugate base more stable than the ethoxide ion? Because if we can understand that, then we will know why acetic acid is a stronger acid. We need to understand why the conjugate base is more stable. For one thing, the acetate ion has an extra carbonyl group that the ethoxide ion doesn't have. This carbonyl group withdraws electron density away from the oxygen with a negative charge. As it pulls electron density away from it, it weakens the negative charge on that oxygen, which means that oxygen doesn't really have a strong affinity for a hydrogen ion, which makes it a more stable base. So that's one reason. It's the inductive effect of the electron withdrawing capabilities of that carbonyl group. Now, there's another reason too, and it's called resonance. Ethoxide doesn't have any resonance structure, so the negative charge is localized on its oxygen. The electrons on that oxygen, they're localized. They can't move. They're stuck to that oxygen atom. But the electrons in this oxygen, they're shared with this one. Whenever electrons are shared between multiple atoms, those electrons are said to be delocalized. They're free to move around between multiple atoms. And typically, whenever you have electrons that are delocalized, typically you can draw resonance structures. So this oxygen can take two of its electrons, or a lone pair, and form a double bond, causing this pi bond to break, pushing two electrons on the other oxygen atom. And so we're going to get a resonance structure that looks something like this. So now the negative charge is on the other oxygen atom. These two are known as resonance contributors. The actual molecule, it's somewhere in between those two contributors, and it's called the resonance hybrid. Now, how can we draw the resonance hybrid? To draw it, you need to know what bonds remain in their location and which bonds can break. So in both structures, each oxygen will have at least one bond. Now notice that sometimes this one will have two bonds and sometimes this one will have two bonds. So that extra bond is going to be shared between the two oxygen atoms because it can move around between both. Now notice that this oxygen atom has a negative charge, and in the other example, the other one has it. So really, they're both sharing the negative charge. What you do is you write a partial negative charge on each. If the total charge on a molecule is -1, and the two oxygen atoms are sharing that -1 charge, then the average charge on each oxygen atom is about -1/2. But you can say it's partially negative to represent a fractional charge. And that's another reason why the acetate ion is more stable. As you can see, this oxygen bears the entire negative charge. But in the acetate ion, that negative charge is shared between two oxygen atoms, so it's weakened. It's not as strong as a full negative charge. Now let's move on. Let's talk about cyclohexanol and phenol. Both of these molecules contain a hydroxyl group. The only difference is phenol is part of an aromatic ring. It's attached to a benzene ring. Now, which of these molecules is more acidic? Is it the one on the left or the one on the right? The pKa for cyclohexanol is roughly around 16. It's very close to ethanol. But for phenol, it's much more acidic. The pKa is 10, which means phenol is a stronger acid. Now, if phenol is a stronger acid, that means that it has a more stable, weaker conjugate base. So let's draw the conjugate base for these two molecules, and let's see if we can understand why the conjugate base of phenol is much more weaker or more stable than the conjugate base of cyclohexanol. So this is called the phenoxide ion. And here's the other one. So notice that the electrons in this oxygen are localized. They can't move around. There's no resonance structure that we can draw for the conjugate base of cyclohexanol. That's why it's less stable. And this oxygen bears the entire negative charge. Now, if you look at the conjugate base for phenol, we can draw resonance structures for this molecule. The negative charge is not localized on the oxygen. It can be shared between many atoms. That is, many carbon atoms in this benzene ring. And let's prove it. So where can we move the negative charge? The first thing we could do is take a lone pair from oxygen, form a double bond, and that's going to cause the two electrons in this pi bond to jump on that carbon. Whenever you draw a resonance structure, you want to indicate it with a double-headed arrow. This double-headed arrow tells you that you're drawing a resonance structure. Now, the resonance structures that we drew for the acetate ion, those structures were equivalent. They were the same. But notice that these two resonance forms, they're not the same. One is more stable than the other. And when you get into a situation like that, sometimes you need to identify which one is the major resonance contributor and which one is the minor resonance contributor. The major resonance contributor is the resonance form that's more stable. So looking at these two resonance forms, which one is more stable? Is it better to put a negative charge on a carbon atom or on an oxygen atom? It turns out that oxygen can stabilize the negative charge better than carbon can. For one thing, oxygen is more electronegative, and typically it's bad to put a charge on carbon. You'll find that it's not very stable to do so. So it turns out that this resonance form is more stable, so it's the major resonance contributor.